In order to analyze rotational motion, we first need to study how to describe rotational motion. And we'll begin by defining a term that we've already defined for linear or translational motion, and that's position. If I think about a car driving along a road, I can define some initial position of the car. I'll just go ahead and call the front of the car here some x initial position of the car. And maybe, after some time the car is driving, it ends up at this final position right here. So I'm just going to go ahead and call that x final. So if I have an object that's rotating instead, I can define an initial position and final position based on the angle of rotation of that object, right? And so I'm going to overlay a degrees grid on the back of this vinyl record on the right here, so we can track how the angle of this vinyl record is changing. All right, so I've gone ahead and drawn like a red imaginary line on the record so we can keep track of where it's rotating visually. Since it's starting at this like 90 degrees position essentially, I could just call that my theta initial. So instead of x, we'll use theta to define what we're going to call the angular position of the record. And then if I were to play this record, let's go ahead and play it for a little bit. And then maybe as the record's rotating, we stop it when it gets to about, I would say 240 degrees. So that'll be the position of the record. That red line now is pointing at 240 degrees. And so the record has rotated from the 90 degree mark to the 240 degree mark, right? So I'll go ahead and draw on my diagram now. We said that this right here was like theta initial, right? And then this would be my theta final. So in this case, theta represents the angular position of the record at any point. Now, in the case of linear motion, I also defined a term called displacement, which was nothing more than the change in my position. And so if the car started at x initial and ended at x final, I could say that the displacement would just be a straight line from the initial to the final. So I can go ahead and just draw in a line here, and that would be my delta x. And mathematically, recall that delta x can be found by taking the final position and subtracting from it the initial position. And so I can do something very similar for rotational motion. I can define something called angular displacement, right? And that's nothing more than saying how many degrees, or in this case we're using degrees, how much of an angle did the record rotate through, essentially? Well, if I started at 90 degrees and ended at 240 degrees, right, then I can show that on the record like this, right? This would be my delta theta. I'm going to go ahead and just draw that curvy arrow to show that, hey, the record started at a position of 90 degrees, and it rotated until it ended at an angular position of 240 degrees. So delta theta is going to be the same thing as delta x in this case. It's going to be theta final minus theta initial. So mathematically, that would be 240 minus 90 degrees. That would be 150 degrees. And so the angular displacement of the vinyl record would be 150 degrees. In other words, it is now 150 degrees more rotated than where it began. All right, let's go ahead and apply this same logic to define a velocity value for rotational motion. When we studied linear motion, we defined the velocity of an object to be the displacement of that object in a given amount of time. And so in other words, if the car on the left here is beginning at some x initial and ends at some x final position, the displacement of that object, shown here as delta x, divided by the time that it took the car to travel from the initial position to the final position, would be that car's velocity. And we used the letter v to represent velocity. Now, we can do the same exact thing for rotational motion, but this time we'll use the change in angular position over time. And so if I were to say this vinyl record is rotating from theta initial here at 0 degrees to theta final at 90 degrees, and I knew how long it took the record to rotate through that angle, then I could say that the change in the angular position, or the angular displacement, divided by the time would be what we're going to call angular velocity, represented by the Greek letter omega. Now, omega looks like a W, but it's not a W. It's a Greek letter, and it's lowercase omega here. So I'm going to define these below, but again, Linear velocity we represent with a v, and angular velocity we represent by the Greek letter omega. All right, now let's go ahead and define one last angular quantity, angular acceleration. All right, now in linear motion, we defined the acceleration of an object to be the change in the object's velocity over time. And so, as an example, let's say that you were running along a path in a straight line. If an object is accelerating, we would expect that object to cover more distance every second than the previous second. And essentially, our velocity is increasing every second. And if our velocity is the rate of change of our position over time, that means that every second our position is changing by a greater amount. So I might imagine maybe the person after 1 second is, let's say they're right here, it's right like that. And then maybe after 2 seconds, they're over here somewhere. Okay. And then maybe after 3 seconds, they're over here. And I'll go ahead and label this as maybe that's 1 second. This is 2 seconds. This is 3 seconds. And so I see here that the delta x, right, this could be my delta x1, this would be my delta x2. These are getting larger and larger. And so we would say this object is accelerating because its rate of change of position is increasing over time. In other words, if I were to calculate the velocity at each point, right, this could be velocity 1, make that a 1 here, velocity 2, then, velocity 2 is going to be greater than velocity 1 and so on and so forth, right? This would be delta x3, and the velocity here would be greater than the velocity at point 2. So it's increasing its speed. So we said that the acceleration of an object was the change in its velocity over time, right? And everything we've done in this class so far has been for uniform or constant acceleration, so that a is not changing, right? So this is going to be a constant. That means that every second my velocity is going to increase or decrease by the same amount. We can do the same exact thing for rotational motion. This time instead, I want you to imagine that this disk is spinning and it's starting to spin faster. So when you see it, you might just say, oh, this looks like it's spinning faster, or it's rotating faster every second. So it might look something like this. Maybe after 1 second, you rotate the disk, and this is my theta, right? So this could be like my theta, initially, and then maybe this is theta after 1 second, right? And then maybe you keep spinning the disk, and now it's covered a larger angle. So this could be like my theta at 2 seconds. And then maybe, let's go over here. Let's say that's like theta here. Right, this could be theta after 3 seconds, and then so on and so forth. So it's going to cover a larger angular displacement. This could be like my delta theta 1, my delta theta 2, delta theta number 3. And again, if we take this delta theta and divide by the time, if each one's 1 second, right, this could be, I'd have an omega 1, that's my angular velocity during that portion. This could be the angular velocity during this portion, that's going to be bigger than my angular velocity during the first portion, and so on and so forth. So as you see, the vinyl record is rotating through a greater angle every single second. That's what we call angular acceleration. Just like a person running, they're getting farther every second than they were the previous second. This would be analogous to rotating faster. And so we can use not an A, but another Greek letter here called alpha. Looks kind of like a fish. And alpha is going to be the change in, you guessed it, probably not V, but omega over time, right? And so this is our angular acceleration term, alpha here. All right, so now we've defined position, velocity, and acceleration values for rotational motion.